it is modeled, it is predicted that if an astronaut happens to be in the wrong place where the magnetic field from the sun is going through where the astronaut is, the dosage that is allowed in the blood-forming organs that the astronaut would be subject to would be reached within half an hour. So that is, I think, for a 30-day limit. So definitely, if we're going to have human exploration in deep space, we need to figure out a way to know precisely and how solar eruptions occur and what to do with it. And these are unsolved problems. And then you get the magnetized wind, the solar wind, and the ejections. Okay. There's another reason we like to study the sun. By the way, one of the reasons for me is that it's really beautiful. But this is a Venus transiting the sun, and it's one of the rare instances that we can see a planet transiting a star, and we can see it in detail. And we care about planets transiting other stars because the Kepler mission, NASA's Kepler mission, has been looking at the little dips in the lights of other stars for detecting planets around them. And it's amazing that now, 10 years ago, extrasolar planets were a rare thing, but now more than 4,000 have been discovered. And so that begs the question, are these planets habitable? This is a beautiful rendering of the different exoplanetary systems, not all of them here in this one shot, that Kepler has discovered. And the color coding of the planets shows what is the predicted surface temperature of the planet if it's in equilibrium. So based on the distance from the star and the radiative output of the star, what would be the temperature? And typically when we want something that is in the habitable zone, we want planets where the surface temperature allows for liquid water. That's what people mean by habitable zone. But is it a sufficient criterion? From what you've just learned about space weather, you can imagine if the Earth were much closer to our star, and if our star were much more active, then perhaps space weather would make it difficult for life to thrive. And so that's one of the big thrusts of research these days, is to combine what we know about space weather and exoplanets and astrobiology to find the criteria, the bounds that would be suitable for life. And space weather from the star plays a big role, potentially plays a big role. Especially since some stars rotate much faster than the sun, and because of that, they tend to have stronger magnetic fields. So what we learn about our star matters for discovering our place in the universe. I'd like to spend the remainder of my time talking about the exciting observatories and missions that will transform what we know about the sun. And there are still many things we don't know. With SDO and with other missions like Hinode and Iris that I haven't had a chance to talk about, we've learned a lot about how the magnetic field evolves. We've come up with models, but there's a lot of the sun that we still don't know, and we're not at a reliably predictive capability about space weather just yet. But even beyond that, learning about the basic plasma physics that's happening on the sun is relevant for understanding what happens in the rest of the universe. So, the Inouye Solar Telescope had its first light in December, and they released the first pictures. This is a 4-meter primary. This is a telescope with a 4-meter primary mirror on Haleakala. It's the most advanced and biggest solar telescope that we have, funded by the NSF, and it's amazing. So this is the first light image of the surface granules, the granulation patterns on the sun from the Inouye Solar Telescope. You can see a map of the US here for scale. So yeah, each of these is a big state. And look in detail, in between the cells, there are these bright points, bright ribbons. And these are actually regions of magnetic field also, except they're not as strong as the magnetic fields in sunspots. They can still be buffeted by the convective flows. But these regions have been discovered and reported and studied in the past, but not at this exquisite detail. But even though this looks extremely impressive, you ain't seen nothing yet. Because remember, when we want to measure the details of the solar atmosphere, especially its magnetic field, we actually want to measure certain properties of light, how polarized it is. And it's in this polarized light that we can find out a lot about the magnetic structures, how these magnetic bundles might be spun up, how they might generate waves, how the waves might dissipate to heat the corona. So when we get polarized images and spectra from DKIS, that's when the fun really begins. And we're all very excited. We're very excited about Parker Solar Probe. A word about Parker. So in 1958, Eugene Parker, professor at Chicago, demonstrated that a multi-million degree corona, solar corona, necessarily causes an outward flow, which is now called the solar wind. That was the beginning of space plasma physics. And this is an introduction to a journal issue, in the Astrophysical Journal, that was just published on February 3rd, with 50 papers on new results from the Parker Solar Probe. And it was written by Marshall Nogelbauer, one of the pioneers of the field of space plasma physics. I mean, it's fine that he came up with a theory to predict solar wind, but it means little if no one would dare to confirm it. And she did so beautifully with the data from the Mariner 2 spacecraft in 1962. But what Parker is designed to do is to get as close to the sun as it is reasonably possible. It will fly into more and more smaller orbits, and it will get eventually very close, and I'll tell you how close later. One of the early discoveries is that when it measures the magnetic field in space locally, we're not talking about images of the sun, but when it's going through interstellar space, it measures the magnetic field and the particles. It finds that there are actually large deviations of the magnetic field direction, very sudden, and then reversal back. So these are called switchbacks. And this was a surprise to people who study the solar wind. Where does it come from? Maybe it comes from little small magnetic fields that are on the surface of the sun, causing magnetic reconnection, causing jets. We don't know. But that's why we need to have both DKIST and Parker Solar Probe. And you also, of course, need the Solar Dynamics Observatory to complete the picture. But we're learning about how the solar wind is generating, how the sun loses its mass. And in losing its mass, it's losing also its angular momentum. And when it loses its angular momentum, a star spins down. And it's important for us to understand how stars spin down, because we want to know how active other stars are. And if they're spinning faster, they're more active, and it might not be good for life. So we really want to know the history of angular momentum evolution in stars. So that's another reason why Parker's probe is so important. Eventually, you'll get this close to the sun. So it's not right there, like some pictures show you, but it's close enough that it really, really probes the higher corona of the sun. And then, yesterday, we celebrated the launch of Solar Orbiter. The Solar Orbiter will also get sort of close, not 10 solar radii, but up to 30 solar radii, I think. But the most special thing about Solar Orbiter is that it will go out of the plane, the ecliptic, where the planets are circling the sun. So using a series of slingshot maneuvers, using a series of slingshot maneuvers from Venus, it will eventually have an orbit that is inclined from the ecliptic so that we can look down at the northern poles of the sun and the southern poles of the sun. And these are regions that we have not measured very well because it is hard. Even though the sun's axis is tilted by about 7 degrees, so that every now and then we see a little bit, we don't measure the magnetic fields in the polar regions of the sun very well. And that matters. That matters because it affects our models of the solar cycle. It matters because the solar wind coming from those polar regions have a large impact. They shape the heliosphere, affects our models of how coronal mass ejections might propagate. So it has huge importance that we can measure the poles from above and below. So, in one way or another, you've seen different images from the Solar Dynamics Observatory in different colors. And the different colors, these are false colors because most of these are not visible. They show different things. We pick different wavelengths so that they show emission from atoms, like iron atoms, that are like 18 times ionized. They lost 18 electrons. But they lost 18 electrons because it's in plasma that is like 10 million Kelvin hot, very hot plasma. And when we see the solar corona at different temperatures, we find that it is very, very much structured, looks different from one wavelength to another. And combining all this, we can have accurate measures of the temperature distribution and the mass distribution in the corona and study how corona heating occurs. And so there's been a lot of work in that. And to end, I will again shut up and let you enjoy this video.